Okay, last video. So a lot of talking in this video, guys, but real important stuff. These are a lot of cautions that we need to be very aware of because we can run into problems with our description using either how we describe and or how we choose to use our correlation. Okay, so we do have to be very aware of these things. Okay, some of them are obvious and some of them are not. And some of them are not going to totally hurt us, but some of them can lead us down a wrong path, okay? So the first thing is more of a fact, not a caution. So correlation, your R value, it does not make a distinction between explanatory and response variables. So I put the formula back up, okay? You're straight multiplying here, okay? Which means it doesn't matter how you put in X or Y, you're going to calculate the correlation correctly, okay? Next thing is also more like a fact. So because R uses standardized values for observations, R does not change when you change the units of measurement for X, Y, or both. Okay, so if you're going to choose to measure your height in centimeters versus inches, okay, and then weight in terms of kilograms versus pounds, or one but not the other, okay, if you're going to change one or not the other, or both of them, it's not going to change the correlation between the height and the weight, okay? And this next thing is also more of a fact about correlation. So the correlation itself, it has no unit of measurement. It is simply just a number, okay? The next few things that we're going to talk about, okay, they're describing, we have to keep this in mind, that describing the relationship between two variables is more complex than describing the relationship or the distribution of one variable, okay? We need to kind of keep certain cautions in mind when we use our correlation, okay? So, very, very important that correlation does not imply causation. So even when a scatter plot shows a strong linear relationship between two variables, we cannot conclude that changes in one variable cause changes in the other, okay? So this might seem a little ridiculous, but if you're looking at data from the last 10 years, you're going to see that there's a really strong positive relationship between the number of high school students who own a cell phone and the number of students who pass the AP statistics exam. Does this mean that buying a cell phone will help you pass the AP exam? Not likely, okay? Instead, it's more that there's a correlation is positive between both variables because they've increased over time. So not as many stats classes were available. The test was not as popular. Not as many people signed up for the test. Now they do. Cell phones were not as common, okay? Now they are. So it's not that there's a relationship necessarily between each other, just that these things both increased over time. More cautions to look out for. Correlation requires that both variables are quantitative. So I'll go back to talking about to what that formula looks like, okay? If both weren't quantitative, you would not be able to even calculate your R value, okay? So the arithmetic in the formula just simply makes sense only if the both of them are numbers, okay? You can't calculate a correlation between the incomes of a group of people and what city they live in because city is a category. It's not quantitative, okay? Correlation only measures the strength of a linear relationship between two variables. Correlation does not describe curved relationships between variables, no matter how strong the relationship is. So a correlation of 0 doesn't guarantee that there is no relationship between the two variables. It just says that there's no linear relationship. Okay. A value of r close to 1 or negative 1 does not guarantee a linear relationship between the two variables. A scatter plot with a clear curved form can have a correlation that is close to 1 or negative 1. So you saw that in that SAT problem. So the percent taking the SAT and the mean SAT score, okay, it was close to negative 1, but the association was clearly curved. So a thing to watch out for this one is that you need to always make sure you know what that graph looks like. You know what the plot looks like, okay? So you can't just interpret R without seeing what the plot looks like. They go hand in hand. The number only means so much if you don't know what it looks like. Okay. Like the mean and standard deviation, the correlation is not resistant. So R is going to be strongly affected by a few outlying observations. So you have to be very careful when you're going to use R's if you see outliers in that scatter plot. It doesn't mean that it's not going to be appropriate to use it, but if there are a lot or strong departures, you have to be careful with your R. And finally, correlation is not a complete summary of your two variable data. So often when you are reporting your R value, you should also report your means and standard deviations of both your X and your Y. Okay, that's it. We'll take a look at tons and tons of examples in class for the entire chapter, but this is it for your preview.